Once again, my name is Sanghoo. I'm working at Korea Advanced Institute of Science Technology, KAIST, and um, I'm working as a assistant professor in my department, Nuclear and Quantum Engineering. And today I'm going to talk about recent progress on radio frequency ion cluster development at KAIST-APRIL. Yeah. So April is my the name of my laboratory. So it means Applied Plasma Research Innovation Lab. Okay, Applied Plasma Research and Innovation Lab. Okay. So actually, this is my second time visit um, this country. So I think around 10 years ago, I attended some physics, project physics conference. It was ICPIZ in Granada. And I had a good memory to visit this country. And this is my second time for a visit. And, and it was very nice weather and nice place and nice season in this period. So it will be a good chance to visit a very nice university. Okay, so let me start with the brief introduction to our institute. So KAIST is actually one of universities. So it's the specialized university for science and technology. And so this is public university under the Ministry of Science and ICT. But however, all other universities in Korea actually belong to the Ministry of Education. So I think we have some science and technology institute, right? So KAIST, GIST, or DGIST. And this is one of the prestige Korea university. And it was established in 1971. So we are a 50-old institute in 2021. So it took around 50 hours from Seoul, and our KAIST is located in the Daejeon city, the middle of the South Korea. So here you can see a very brief map around these East Asia countries, China, Korea, and Japan. We are here. We have borderline here, and here, this part of um, area is our South Korea. And Daejeon is the middle of this South Korea, and then we can move to Seoul by train or bus, and then we can use a flight to the to be here. And here we have some numbers about KAIST. So currently we have students with these numbers, so 11,000, around 11,000, and evenly distributed to all courses, bachelor's, master, and PhD students. And also we have this number of alumni of KAIST, and here you can see very large portion of the PhD alumni from KAIST, so around 50,000, 15,000. Okay. And also, currently we have almost around 700 faculty members without any medical schools. So this is this is a large number of faculty members in Korea, I think. And so this is why we KAIST are first ranked in in Korea. And here you can see the QS ranking of KAIST and the world university ranking of KAIST here. And among these 700 faculty members, we have only 5 faculty members for fusion and plasma research, and only in the Department of Nuclear and Quantum Engineering. And so here, Professor Che is leading us for the plasma and fusion group. And here you can see my picture here. So all these 4 faculty members are interested in the fusion plasma, and I'm specialized on the low temperature plasma, including the electric propulsion. Okay. So, and let's move on to the my lab introduction. So this is our main campus in the Daejeon city. So you can see here main gate of KAIST, and then you can walk around this campus, and then through this the main street you can um, find our building. So here you will see mechanical engineering and Department of Nuclear and Quantum Engineering, and also aerospace engineering on this site. And here, this picture is about our building, so N71. And here you can see where is our my laboratory. So you can see, so you can guess where is my laboratory on this picture. You can guess it, right? So we actually occupy these two rooms, bright rooms. Okay. So, and here are my students, and we sometimes have the annual parties like strawberry parties in KAIST, and Korean barbecue we commonly enjoy. Okay, so we have currently 11 students, so 7 students for PhD course, and we have 3 students for master course, and we have 1 research staff, Mr. Kim. Okay, so first of all, I'd like to show you what we are doing in our laboratory with my students. Okay, so actually, I have expertise on the atmospheric pressure plasma with the specialized the plasma diagnostics. So when I categorize the research topics you are doing in my laboratory, as a first of all, the first part of our research is basics of low temperature plasmas. So, for example, we are measuring some ionic wind produced on the surface due to the plasma by building this kind of the laser diagnostics. So with using this particle image velocimetry, we can visualize the flow structure produced by the dielectric barrier discharge. So more recently, we are studying on the the difference between Earth condition and Mars condition. So we are wondering how this flow structure can be changed on the Mars environment. So currently we are doing such kind of studies, and also we are doing some measurement for quantifying plasma we produced. So for example, by using optical emission spectroscopy, especially continuum radiation, we can measure very simply electron temperature distribution by using very low price commercialized DSLR, and in conjunction with the color filters. Okay, so as demonstrated here. And more recently, we developed a new laser absorption spectroscopy for quantifying helium metastable state. And using this, we can conduct such like nanosecond reserved 2-dimensional imaging or 3D imaging of the plasma jet we produced at ambient air. At the atmosphere pressures. Okay. Okay, next, we are focusing on the plasma-liquid interaction. So we are wondering what happens to the water surface when it imposed by plasma jet. So you can see some difference between water deformation depending on the plasma operating conditions. And also we are focusing on the chemical characteristics in the plasma jet interactions. So as you see here, so we are studying about the chemical dynamics or transport of the plasma jet liquid system, as you see. And also to do such kind of research, we are developing some new optical absorption spectroscopy, and we are commonly suffering from this spectroscopy about the spectral analysis. So we recently we developed the very fully automation of the spectral analysis using AI technology. So, for example, when we input our 2D two-dimensional image in our trained model, we can extract a feature of the two-dimensional image from the spectral data, and then we can get a physical and chemical information from the two-dimensional spectral data, as you see here. So this is very small, but so this black one is experimental data, and this the red solid line shows the AI generated spectrum we have. Okay, so very similar. So very they are matched very well. Okay, the third one is metamaterial based plasma control. So as you see, in the plasma industries, we sometimes suffering from the edge uniformity. So we need to control or monitor the plasma uniformity outside of the chamber. So for example, this focus due to this focus link, the plasma uniformity can be reduced over time. So we can compensate the such kind of the weakness. So by using some technology, so we can control the bias of the electrode or control the impedance of the focus link, and then we can improve our uniformity of the CCP or ICP plasma. And also the next we can we are studying about the metastable based active plasma control. So we are doing simulation and also experiment. So using such kind of metamaterial, we can actively control the electric field or magnetic field inside the chamber, and then we can actively control the plasma we want to control based on our the visualization. Okay, so the last one is ion beam engineering. So we are interested in developing RF graded ion thruster based on simulation. So this is the what I will show you in this presentation. And more recently, we developed the prototype of graded ion thruster we designed. So this is our first very first picture of this xenon ion thruster. And also we are interested in the ion beam etching for semiconductor processing. So with developing the laser-induced fluorescence, we can control the ion beam with the slick grid like this. So we are doing this along with the ion thruster engineer. Okay, so to do such kind of research, we are developing our own diagnostic facility. So first of all, we develop a tunable diode laser absorption spectroscopy TDLS for quantifying helium metastable. And so this is our schematic. So when we put the our plasma of interest with the XYZ stage, you can see here we can measure the very precisely nanosecond image of the metastable state produced in the plasma jet. And we are also developing laser-induced fluorescence for measuring ion energy distribution. And especially, we are interested in measuring argon ion. So we use such kind of scheme. We recently developed this argon ion LIF system for 2D axis measurement. So when we use this for quantifying ion beam source, so we can actually measure like this. So when we control the piezo voltage of the laser, we can shift the laser wavelengths like this, and then we can scan um, when scanning the laser wavelengths like this, we can measure very precisely such kind of ion energy distribution. Okay. And also, we are developing laser Thomson scattering measurement for absorbing the electron information in plasma. So this is our compact-sized Thomson scattering system used by using the Bragg grating filter. So three series of the Bragg grating like this. So this is our the common spectrum when we measure the Thomson's signal from the plasma. And we have to block so very high intensity Rayleigh scattering like this. So when we use the Bragg grating filter with an optical density of 3, and we can cut off our Rayleigh scattering signal very effectively. Okay, so this is very compact size, and this is a very cost-effective method. So with this Bragg filter series, we can use just single spectrometer combined with the ICCT camera, and then we can the Thomson scattering spectrum like this. And when we synchronize other instruments, we can conduct time-resolved or phase-resolved measurement for electron density and temperature, and also energy distribution at low energy part. And also, as you see here, we normally suffering from the very noise data when we capturing the Thomson signal. So we have to conduct with this system with using the Bayesian model. So always we need a statistical analysis about this spectrum. So with this spectral data, we can determine the electron temperature, density, and the distribution function, as you see here. So according to the Bayesian model, and then this alpha value of 2. So when this alpha value grows to the number 2, means the energy distribution function is close to Maxwellian distribution. And also, we are developing some electrical probes, including color probes using the positive frequency. And also, we are developing our own RF compensated Langmuir probe, as you see here. So, very good measurement for electron density and temperature. Oh, sorry. So some plots are wrong here. Okay, so as you see, we have expertise on the low temperature plasma with several diagnostic facilities, and in Korea community we have we have many expertise on. So we have many experts about plasma physics, including nuclear fusion, microelectronics, and also some of people are studying about plasma-assisted environmental and chemistry applications. And however, in Korean community, we have to expand our size regarding the space application. So actually, Professor Wano is pioneer scientist in this field, and even around 10 years ago, he's the only person who are studying about the plasma space applications. But we need to expand our size of the community, and Professor Hora Kim and me will start to join this field. Okay. So this is the brief introduction about the gridded ion thruster and the Hall thruster. So as you see here, so among the electrostatic, so we have actually nowadays many different types of electrostatic thrusters, but we have two types are considered mature and space proven technologies. So the first one is gridded ion thruster, and the second one is the Hall thruster. And here I listed here some special characteristics about the ion thruster and Hall thruster. And here you can see gridded ion thruster has a very high specific impulse compared to the Hall effect thruster. So it's gonna be used for a very specialized mission, space mission in Korea. So we have some plans for the future. However, as you know, because the current density limit in the grid system, so it has naturally has a very low power density compared to the other electrical propulsion technology. So this makes gridded ion thruster bigger than the Hall thruster normally. And this is the underpinning principle of the ICP type ion thruster. So we have many kinds of the method to generate the plasma inside the plasma chamber. So when we use DC plasma, we can call it. So when we use DC plasma, we can call Kaufman type, and then we can choose our radio frequency, power, or microwave excitation, and then we can find many well established types of ion thruster. For example, RIT, many different versions of RIT, and Hayabusa 1 and 2. Okay, and here is a very simplified schematic of the radio frequency ion thruster. And when we use the radio frequency antenna wrapped this kind of cylindrical tube, this chamber, and then we can induce time varying magnetic field and electric field, and we can expect it electron impact ionization, and then we can extract our ion beams with the DC-biased graded ion, as you see here. So this is the potential curve over the spatial dimension, as you see here. And so first of all, we need to summarize some very well-proven technology. So here you can see the very high quality commercialized radio frequency graded ion thrusters using, so for example, so RIT series and PUSAC and GT50 and other things like this. Okay, and they use very different types of gas, so propellant gas from xenon to iodine and as well as water. And also you can see very different thruster depending on the power and many different types of cathode types, as you see here. And so with our Korean colleagues, we need to, for the first, we need to develop our own ion thruster with some a few tens of millinewton level thruster. So we can select, we can refer to the design of our or something this commercialized ion thruster, and then and with the very detailed dimension of these thrusters, we can select our the design parameters or factors to design our prototype of the ion thruster. And as you know, we need to determine the design factors first, depending on our purposes. So first of all, we need to select the coil configuration. Okay, so so actually, for example, we can choose planar coil or cylindrical coil, as you see here, but according to the literature, there is no big difference between these two types of coils regarding the thruster performance. So most RF power source uses a cylindrical coil. Okay. However, in the viewpoint of the plasma physics, actually the planar type coil is better than the cylindrical coil, but for the feasibility, so we can choose cylindrical coil. So you can easily find many different types of cylindrical coil instead of the planar coil. And also for the coil structure, we have to determine the coil turn, the number of the coil turn and minor radius of the coil and coil length to optimize our RF efficiency. And by other factors, and also we need to confirm the quality factor of the RF antenna as well as inductance of the antenna we designed. Okay. And also we need to select our chamber geometry. So for the geometry, we can choose the factor. So we have chamber's diameter, and we need to consider the skin depth of the RF heating. So because we use the ICP type plasmas, okay? So considering the skin depth determined by plasma characteristics, we need to select our rim depth or the grid structure depending on the skin depth of the ICP plasma. And also with the coil optimization, we have to choose chamber height, as you see. And also we need to very carefully design about the gas diffuser. Okay, so baffle structure can increase the residence time of the gas inside the chamber. It is very important to sustain a plasma. So because electrons should collide at least one before it loses inside the chamber or the grid. So the baffle geometry determines the electron temperature and density, and as well as the electric or magnetic field profiles inside the chamber. So we need to simulate the baffle's geometry with a plasma. Okay, so when we before we determine the gas diffuser, we need to test our geometry, baffle geometry, with a simple numerical simulation, like things like COMSOL multiphysics with a heat transfer and also rarefied gas dynamics. Okay. And the last one is power and mass flow, and they are also very important for operating the radio frequency ion thruster. So we need to confirm the optimized power and mass flow of the xenon or propellant gas, considering all kind of geometry. Okay, so with the simple numerical simulation, so numerical simulation help us to optimize all these kind of design factors prior to the manufacture of the prototype of the ion thruster. Okay, so first of all, coil structure. So we can choose planar type or cylindrical type coils, as you see here, but these two upper side graph shows the profiles of electron density and temperature, and the bottom side shows the cylindrical cases. Okay, so as you see here, when we choose planar type, you can see a very flat, very uniform electron temperature inside the chamber. However, when we choose the cylindrical type coil as a RF antenna, you can see very non-uniform, non-spatially uniform profiles of the electron temperature. So according to this result, we need to using this planar type coil, but the cylindrical coil is much advantageous to manufacture or maintain the what can I say? So the coil structure. Okay, so the cylindrical type is much more suitable for RF thrusters. And also, we are focusing on this gas diffuser, so-called baffle. So, as I mentioned, the gas distribution is the most important factor that we have to determine through experiment. But also, you will see there's very little information about the effect of the baffle geometry or gas injection. So, and also you can easily find many different types of the gas distribution inside the chamber. So there's no unique solution so far, I think. So as you see here, so normally RIT choose this kind of gas injection system. So as you see here, so this small part depicted by this red box is very plus the radially distributed gas injection on the backside of the ICP chamber. And also Burfitt select such kind of very abnormal gas diffuser, I think. So because this kind of diffuser can disturb the plasma uniformity because the RF antenna placed on the same plane in the gas with the gas diffuser. And also sometimes you can see very interesting gas diffuser like this. So this type of radio frequency ion gradient thruster choose this type of the gas diffuser. So you can see the 3 holes, the very exit very close to the grid here. So I don't understand what they choose such kind of method for inject the gas propellant. So when we design our own ion thruster, we need to confirm our design factors we selected. So first of all, we need to develop our own numerical simulation through the consumer multiphysics. So here you can see very it's a little bit tricky. So because we fully not fully, but semi-coupled simulation models combining with these 3 different physics models. Okay, so we selected here free molecular flow to simulate our rarefied gas inside the chamber, and also we choose plasma and magnetic field models, and also to simulate our ion beam. The charged particle tracing model was used for our simulation. And so I have not enough time for describing all these physics model used for consumer multiphysics. You can find details about the physics equations or description in the document provided by the consumer multiphysics using this QR code. Okay, and so first of all, we need to solve the pressure distribution inside the chamber and outside the chamber like this. And also, so this stationary solver give us Zeeland density or pressure distribution inside and outside the chamber. And using them, we can we can input this data into the second models, and then we can simulate the plasma we can solve the plasma characteristics as you see here with the tailored the computational domain. And in this ICP model, we can obtain the stationary um, solution about the xenon ion density or ionization rate distribution and also electric potential. So using them as a input data to the charge particle tracing model, and then we can describe the ion trajectories or energy or velocities so passing through the grid system. Okay. So this is our ion thruster in the computational domain. So in the mirror image in the left side, you can see some parts and the materials depending on the parts we selected. And here you can see some specific dimensions of our a few tens of millinewton class ion thruster, as you see here. And we tested here our own buffer structure. We can install our own ion thruster in the future. So here is some very fundamental. So this is very simple. The geometry of the gas diffusion. Okay, and also here you can see the grid design for simulation here. So we have 3 grid systems. So this deceleration, acceleration, and also we have screen grid as you see here with a DC bias at these values. And also we employ here the 2-dimensional axis symmetry. So naturally we can see annular slit type grids as you see here. So this is not realistic. So we have to compensate or collect the terms of ion beams passing through such kind of slit shaped grid. So we developed some numerical collection terms. I will show you some next few slides. So first of all, so as a first step, we calculate the rarefied gas flow dynamics as you see here. So with this boundary conditions, we can solve the molecular flux at the model boundaries as you see here. So here you can see 3 types of different boundaries. So here we have vacuum reservoir outside the chamber. Here we can see grid, and we can set our world temperature at 400 Kelvin. And here you can see the outgassing boundary with the specific the gas flow rate as you see here. So here in this case we choose 6 SCCM of xenon gas here. So with these boundary conditions, you can so stationary solver give us such kind of pressure of the xenon gas as you see here. So this is log scaled pressure in the unit of millitorr as you see here. So inside the chamber you can see high pressure compared to the outside the grid system. And as you see, so this 2 plot shows the profiles of the pressure along the radial axis here and the z-axis here. Okay, so as you see, the pressure is high, maintained high values inside the chamber, but outside the chamber, the pressure dramatically goes down like this. And also, depending on the z-axis, you can see very different profiles of the relic. So xenon gas pressures. So it means the aspect ratio of the chamber should be considered, because with the very short depth of the chamber, you can expect the very non-uniform xenon gas that makes very non-uniform plasma properties when we generate the plasma inside the ICP chamber. Okay, and also based on this result, we can input this data into our second model for plasma. Okay, so and this is our model's the simulation result of the ICP plasma. So we here simulate using coil power of 60 watt at 1 megahertz. So the frequency of the 1 megahertz is conventionally used for graded ion thruster. So we choose. And so once again, you can see boundary condition on the left-hand side, and you can see electron density on the right-hand side, as you see here. So some details on the boundary conditions is normally the boundary conditions of the ICP plasma follows the very conventional ICP plasma. So here our gas vector was floated, and also here we have dielectric walls as a charge accumulation system, and also here we have DC biased graded ions, the ion optics, as you see, and here we set open boundary outside the chamber. And we choose plasma and magnetic field models in conjunction with the plasma conductive coupling and electron heat source, as you see. And here, in this model, we considered some collision process, including elastic collision, excitation, and ionization of the xenon gas. And their collision cross-section data was found from LXCAD. Okay. And so on the right-hand side, you can see electric potential and also magnetic flux density, as you see here. So this value of the magnetic flux density and electric potential is quite reasonable, because we applied here screen voltage as a 1000 volt voltage. So it is so you can see slightly increased potential compared to the screen grid bias. And also here you can see magnetic field configuration in this chamber geometry, and also this value of the flux density is quite reasonable. We can see normally in ICP type plasma. Okay. So with this result, so we can use the plasma characteristics as an input data to our charged particle tracing to describe the ion beam characteristics in the single software. So in this case, we have two initial conditions. So we use first one, particle mass. So here we have xenon atom mass as a particle. And also we release about 1,000 particles per 0.4 microsecond to xenon ion like this. So the position of the xenon ion is proportional to the ionization rate we obtained in this model. And then so we can release ion particles inside the chamber depending on the ionization rate, as you see. So this is the GI imaging. So when we release the particle like this, we can simulate the ion beam like this, and we can determine the ion trajectories with each speed close to the ion optics, as you see here. So here you can see it increases up to 45 kilometers per second passing through the grid system, and also we can determine the colliding ions and extracted ions trajectories, as you see here. So some particles colliding with the axial grid surface, as you see, but most of ions passing through the grid as well. Very good. And also, and based on this result, we can determine the number of particles from ICP depending on the grid operation. So you can count the number of ions depending on the surface. So here you can see the colliding ions on the screen grid and vacuum and also acceleration grid. And so using this, we can determine the fraction of the escaped ions. So which means we can get an ion beam current from our ion thruster. And when we determine the the particle speed of the ions, we can finally obtain the thruster values from our numerical simulation. So, and also, as I explained, as I mentioned, we can see slit type grid in this two-dimensional axis metric simulation. So we need two collection terms here. So first one is extraction probability, and the second one is for dispersion angle between the hole types and slit types grid. So by using these two types of collection terms, we can determine this collective thruster depending on the applied grid voltage. And as you see here, when we choose our 60 watt of the ICP, we can expect our RIT performance, as you see, of few tens of the millinewton, as you see here. And we can a little bit overestimate the efficiency for energy and mass utilization, but it is quite reasonable because in this simulation we did not consider any electron sources like the cold cathode. So considering this, these efficiencies are quite reasonable in this numerical simulation. Okay, so based on this numerical simulation, we currently we recently developed our own hardware for prototype ion thruster. So here you can see we designed our own grid system, and so we manufactured this grid as you see here. So on the left-hand side, you can see ion thruster components, and now we manufacture our assembled prototype as you see here. And also with this test vacuum facility, we can simply test our first version of the prototype RIT in my laboratory. So with this system, so this is the backside of the RIT. So the through the vacuum boundary. So we can put here some electrical signals, and also we can inject our electrical probes through these blocks. Okay, and also this is the very first photograph of our radio frequency ion thruster, depending on the grid biased voltage from 300 to 1000 volt here. So you can see as increases the grid voltage, you can see very beautiful xenon ion beam above the grid system. So this is ongoing our ongoing work. So so our experiment. Our design factors are followed by our simulation widget, but there are some issues when we conduct experiments with our first version of the prototype. So first, we need to stabilize and we need to develop our ignition technology for break down the radio frequency plasma inside the chamber. And also, we need to improve our chamber facility because we have a very abnormal discharge like this. So first one, you can see unexpected discharge on the grid system like this. So here you can see very high current discharge between the grid. So this is our first problem. And also sometimes such kind of inhomogeneous discharge was observed. So inside the chamber, so without the grid operation, sometimes such kind of very inhomogeneous discharge can be produced. But these two kind of abnormal discharges cannot be simulated by using any simulation tools. But so we need to address these issues experimentally and through the try and errors. Okay. So when we complete our first prototype in our laboratory, we can move our system to this very high quality vacuum system manufactured in the Korea Aerospace Research Institute. With my colleagues, I will finish our first version of RF ion thruster development. Okay, thank you for your attention.
Thank you very much, Dr. Park. We have time only for a few questions in the audience.
Hello. Thank you for your talk. See, is working? Is it?
No.
Okay. Yeah, now it's working. Thank you for your talk. It was very interesting. And I have a question about the current balance basically that you have in the thruster. So since you are emitting ion particles, so you have to collect electron current somewhere that compensate for these ion emission. Are you collecting these in the screen grid or in the injector? There are several ways to do this. And I was just curious about this.
So you mean during the experiment or simulation?
Well, both.
Both? During this experiment, so during our experiment, we measured the electron current through the grid system. Okay? Yeah, this is very simple method. And also, in the simulation, we choose our charge particle tracing model, right? So in that case, electron was not considered. So, and instead of the electron, we was focused on the ion neutral collision and charge exchange. Yeah, that was some. So we need to consider both kind of collisions during the charge particle tracing models. Yeah. Thank you.
Yes, it worked.
Thank you for your talk. I have a couple of questions. The first one is related to if you perform the comparison between simulations and experiments, if they are comparable, if you achieved the expected current output from the thruster.
So you mean
like if the simulation results are comparable with the current that you obtained from the experiment? The current emitted from the thruster, the ion current.
Ion current, sure, yeah.
Okay.
We need to experimentally measure the ion current outside the chamber, right?
Yes.
Yeah, and we will use them to validate our simulation result. Yeah.
Okay.
But we need to improve our facility for measuring ion beam current and other characteristics to validate.
Okay. Can't you use the current that you measure from the grid, the discharge current?
Yeah, sure. Yeah.
Okay.
Yeah. It must be. Yeah. Right. Thank you.
The second question is related to I saw that in the last slide you showed that you wanted to switch from 13 megahertz to 2 megahertz. Why is that? Is to improve the matching?
Because we have have a limited budget. Yeah, so we choose first of all. So we choose the power. So we use our own power supply we already have. So we need to change our. We need to buy new one.
Okay.
For plating the.
And why 2 megahertz is better?
Because 2 megahertz is commercialized frequency for the semiconductor industries. Yeah.
So you will have to change the coil probably to have the same matching. You will probably have to change the antenna and
Yeah.
redesign it?
Yeah, exactly. Yeah, so we need to slightly modify our design factor of the RF antenna depending on the frequency. So when we choose our 2 megahertz, we need to modify the antenna structure. Yeah, thank you very much.
Last question. Okay, on my side, first I want to congratulate you for all the equipment or the diagnostics that you have, that are very impressive. All you can do with all this, okay? Then, regarding perhaps continue a bit the question by Simone, which is the coupling you have in the simulations between the neutrals and the ions? Because it seems that we are using one module for the neutrals, a different module for the ions, and they are there's a strong coupling between them because you have commented about collisions, ion neutral collisions, but it's also possible a lot of recombination of neutrals of the world that return as ions. So is this coupling between the neutral dynamics and ion dynamics included in your simulations?
No, because this is very simplified model. So when we consider all about the recombination with the walls on the surface and other so minor the collision processes, it's gonna be very the such like a peak simulation, right?
Yeah.
Yeah. Yeah. So
collaboration with your group here.
so actually, basically, I'm
We are doing this type of simulation.
yeah. Basically, I'm a experimental guy. So just we developed these simulations, so very simple tools,
Yeah,
right?
and
So simple method to design our first version of the ion thruster. Okay.
Yes, of course.
Yeah,
Mainly
yeah.
for understanding the experimental results and for design. Okay, fine. Well, this is a seminar of the PhD program for space engineer. Most of the students that are here are PhD students in space engineering. We have very active lab, and perhaps some of them can be interested in having some kind of internships. There are PhD, postdoc. Are there opportunities for them?
Yeah. Okay, sure. It's gonna be okay. Yeah. So I welcome you guys to join our groups with a collaboration.
We appreciate this.
So we have many the diagnostic facilities our laboratories. So I welcome collaboration about the experiment.
Okay, thank you. Let's thank you again our speaker.
Thank you very much.